Today we're going to discuss section 15.6, which is solubility, equilibria, and the solubility products. So we're now moving into part 2 of chapter 15. We've talked about acids and bases, and now we're going to talk about salts. Okay, so we are assuming that an ionic solid dissociates completely, which means it breaks up into its cations and anions. So for something like calcium fluoride, it's breaking up into calcium ions and fluorine ions. This process occurs back and forth until it becomes what's called saturated, which means no more solid will dissolve. And we can also write what's called the solubility product constant. This is similar to case of A or case of B, but in this case we're dealing with salts. And so because calcium fluoride is a solid, it is not included in the KSP. So we're just including the ions. Now remember, we haven't done this in a while because most of our reactions have been 1 to 1 to 1. But because we have 2 fluorine ions, that's why we have the concentration of fluorine taken to the power of 2. A couple things that don't affect the position of equilibrium are the amount of excess solid, because remember, solid doesn't affect equilibrium. Size of the particles won't shift the position of equilibrium either. You can find the equilibrium constants for lots of different salts on table 15.4 in your book. And remember, the solubility product is an equilibrium constant, whereas solubility is an equilibrium position. Okay, so they are not the same thing. So let's look at an example. Let's calculate the solubility product for bismuth sulfide, which has a solubility of 1 times 10 to the negative 15. Okay, so the first thing we want to do is write our reaction. So we're going to have our bismuth sulfide, and it's going to break up into 2 bismuth ions, aqueous, and 3 sulfur ions. And we know that the KSP is equal to 1 times 10 to the negative 15, and we can write that as the concentration of bismuth ions to the second power times the concentration of sulfur ions to the third power. So we're going to set up something similar to an ICE table. This is just, to me, it seems like the easiest way to do it. We know that initially we have a solubility of 1 times 10 to the negative 15, and that before it dissolves in water we have nothing of the ions present. Okay, this is going to completely dissociate, so we're going to subtract 1 times 10 to the negative 15. And to these, we're going to add 2 times that molarity. And then for sulfur, it's 3 times that molarity. And so for equilibrium, we have nothing of our solid left. Here we have 2 times 10 to the negative 15th ions of bismuth left, and 3 times 10 to the negative 15 concentration for our sulfur ions. So if we want to plug that into our solubility product, we have KSP, which is 1 times 10 to, oh, you know what? I think I confused that. Yeah. KSP. Oh, we're solving for KSP. Yeah, I read the wrong thing. Oops, that's our concentration. Okay, so we don't know the KSP. So KSP equals our concentration of bismuth ions, which is 2 times 10 to the negative 15. Make those parentheses, and that's to the second. And then we've got our sulfur ions, which is 3 times 10 to the negative 15, and that gets cubed, and that's coming from up here. If we do the math and plug in solve for that, we should get 1.1 times 10 to the negative 73, and just like before, KSP doesn't have any units. Let's go the opposite direction, and given the KSP, let's find the solubility. Okay, so we have the KSP value for copper 2 iodate, and we want to calculate its solubility. So let's start by writing our reaction. This is our solid. It's going to break up into copper ions and 2 iodate ions. And we know that, let's see, I think we have room here. Our KSP is equal to our concentration of our copper times our concentration of our iodate squared, because of the 2 right here. So let's do our initial change equilibrium. Now the difference here is that we don't know our starting concentration, and so we're going to say that that's X. And we know that initially we have no copper and no iodate. And so here it's minus X plus 2X because of the 2. And so our equilibrium becomes 0, X, and 2X. So now if we plug that into our KSP, which we know equals 1.4 times 10 to the negative 7, that's equal to, from up here, our copper, which is X, times our iodate, which is 2X, and that gets squared. So this ends up being 4X cubed. And if we solve for X, we get that X equals 3.3 times 10 to the negative third molarity, and that's our solubility for copper to iodate. So we can use KSP and go both ways, either solve for KSP or go backwards. Sometimes we can't calculate the actual solubility, and so we need to calculate the relative solubility. There are 2 ways to do this. One is if all the salts that we're comparing produce the same number of ions. So here's 3 salts. We have silver iodide, copper iodide, and calcium sulfate, and they all produce a cation and an anion. So they produce 2 ions, 1 cation and 1 anion. So our KSP is the concentration of the cation times the concentration of the anion. If X equals the solubility, like we did in the previous example, then at equilibrium, X is equal to the concentration of the cation and the anion, and so our KSP is equal to X squared, because it's the cation times the anion. Well, if we want to solve for X, basically by rearranging, it means that we're taking the square root of the KSP. So it's either KSP to the 1/2 or X equals the square root of the KSP. So if we do that to all 3 of these KSPs, we get that the calcium sulfate has the highest value, then the copper 1 iodide, and then the silver 1 iodide. And so this gives us relative solubilities, calcium sulfate having the highest solubility. The second way to compare is if the salts have different numbers of ions. And so here are 3 salts, and they all are going to produce different numbers of ions. Copper 2 sulfide will produce 2, silver 1 sulfide will produce 3, and bismuth sulfide will produce 5. So different numbers of ions. We can't directly compare the KSP values because they are producing different numbers of ions. If we actually went through and calculated the solubilities, though, we would find that bismuth sulfide had the largest solubility, followed by the silver 1 sulfide, and then the copper 2 sulfide. This is opposite the order of the KSP values, and so if your salts have different numbers of ions, take the KSP value that is the smallest, and that salt has the highest solubility. Alright, so far we've been looking at salts that are only dissolved in water. Let's look at salts that are dissolved in water that contain an ion that is in common with the salt. So this is where we're going to hit on the common ion effect again. Let's say we have silver 1 chromate, which has a KSP of 9 times 10 to the negative 12, and we're dissolving it in a 1 molar solution of silver nitrate. So here's our reaction, okay, and we're going to do our ICE again. We don't know the initial solubility or concentration of our silver chromate, so we're going to make that an X. And we know, now normally what we said is 0 silver and 0 chromate. Well, we know that the chromate is 0, but because of our silver nitrate solution, and it's going to completely dissociate, we know that we have 0.1 molar of the silver. Change, we know that our silver 1 chromate is going to completely dissociate, so minus X. This is plus 2X, and this is plus X. And so for equilibrium, we know we're going to have 0, 1, plus 2X, and X. Okay, if we write our KSP, we know that this is equal to 9 times 10 to the negative 12, and that this is equal to Ag plus squared times the concentration of the chromate. And so if we plug in our equilibrium expressions, we get that that's equal to 0.1 plus 2x squared times our x. Now this can get a little complicated, so now we're going to go back to making our assumptions where we said that x is really small, and so that gives us 0.1 squared times x. And so if we solve for x in this case, it comes out to approximately 9 times 10 to the negative 10th, which is definitely less than 5% of 0.1, and so our assumption checks. And so this is our solubility of the silver chromate with the salt. Now if we look at the solubility of silver chromate in just water, it is 1.3 times 10 to the negative 4th, and so this shows that with a common ion, the solubility is depressed because that common ion effect. And so in water, our solubility is much higher than if it already has a common ion present. Let's look at how pH affects solubility. So we looked at common ions, now let's look at pH. pH of a solution can also affect the salt solubility. So we have magnesium hydroxide, and that's breaking down into our magnesium and our OH minus. If we add OH minus, then we're increasing the pH because it causes the equilibrium to shift less due to that common ion effect because we have an OH already present, and if we're adding more, it's going to shift in the direction of the solid. Okay, and so that decreases the solubility because more solid is staying and not breaking down into its ions. If we added H+, which decreases the pH, then it's causing the equilibrium to shift right because that OH minus is going to react with the H+, so now it's going towards the ions and it's going to increase solubility. So decreasing that pH is going to increase the solubility. This is why milk of magnesia works. This is actually the reaction for milk of magnesia, which is if you have like a lot of acid problems with your stomach, it dissolves in the stomach to combat the excess acidity because the H+ is already present there. Okay, this also applies to salts with other anions. So for example, we have silver 1 phosphate dissolves into silver ions and phosphate ions. Well, if you add H+, so if you decrease the pH, we're going to increase the solubility. And the reason that that works is because our phosphate ion is the conjugate base of a weak acid, and so it's a strong base, and so it reacts with the H+ to form HPO4 2-. And so if it's going to react, it's going towards the products and increasing solubility. If we look at another salt, silver chloride is not affected by acid, and that's because the Cl- is the conjugate base of a strong acid, so it's a weak base, so it's not going to react. So in general, if the anion, X-, is an effective base, which means it's the conjugate base of a weak acid, then the salt, Mx, will have increased solubility in acidic solutions. So if you decrease the pH, make the solution acidic, the solubility will increase. Some common ions that this works with are hydroxide, sulfur, CO3 2-, C2O4 2-, and chromate, CrO4 2-. This is also how stalactites and stalagmites are formed. Addition of CO2 to the groundwater makes it acidic, which then increases the solubility and erodes all of the rock. And then once that CO2 goes into the atmosphere, the water now becomes less acidic, and that forms, I think, stalagmites, which come down from the top. So it kind of works both ways. Okay, so here's some problems to work on, and we'll discuss this more in class. Have a good day.